I don't know if it's I think it's recording. It didn't give me a countdown. Oh my gosh. I don't have a countdown. All right, so here we go. Worksheet 3. Now, if you've not done this, you better get it done. So this is the graph, and there's already some stuff on here. So I'm just going to kind of walk through what we talked about for each of these questions and try and do it fairly quickly. So describe in words the motion of the object from 0 to 6 seconds. Well, it looks like for the first 2 seconds, now again, remember, this is a position time graph, and the object is at the 0 position for 2 whole seconds, 0 meters per second, not moving. It's at rest for 2 seconds. Then it starts moving in the positive direction with a positive constant velocity. That's what I would say. The object starts at the 0 position, not moving for 2 seconds, then moves in a positive direction with a constant velocity for 4 more seconds. That's what I would say. Now, you were supposed to also construct a qualitative motion map. So I said 0 position, ... Those represent the 2 seconds that it's not moving. And then 1, 2, 3, 4 arrows that are the same length in the positive direction, indicating that for 4 seconds it was traveling with a positive velocity that's constant. And of course, A is 0. It's not accelerating the whole time. Then they ask for instantaneous velocity at the following times. Instantaneous velocity at 1 and 3 seconds. Well, at 1 second, what is the slope of the line at 1 second? 0. So that is the average, or that is the instantaneous velocity at time 0 seconds. We don't really talk about instantaneous velocity and haven't really. But if it is a consistent slope, then that is the velocity at each of those times. So at 0 seconds, at half second, at 3/4 of a second, at 1 second, at 1.5 seconds. So all of those times, the slope is 0. Then they ask about 3 seconds. So time 3 seconds, how fast? Well, the whole steepness here, this steepness does not change, right? It is the same steepness the whole time. And it is 30 meters of displacement, and that took 4 seconds to do that. So that's where this came from. So I figured out that the steepness of the second part here is 7.5 meters per second, positive 7.5 meters per second. And so that is the instantaneous velocity at time 3 seconds. In fact, any time after 2 seconds, that is the velocity. Then it says, what is the simple average of those two? Well, 0 plus 7.5 divided by 2 is 3.75 meters per second. That's the average of these two velocities. Then it says, what is the average velocity for the entire interval? Well, the total displacement is 30 meters. 30 meters. Why am I here? Let me move me up. Total displacement is 30 meters. Total time that this happened over was 6 seconds. I know 2 seconds it wasn't moving, but that's still the entire interval. So 30 meters over a 6-second time interval, that is a 5 meter per second average velocity, 5 meters per second. Those aren't the same answers. So why are these two values different? Well, one is a simple average, one is an overall average. Which do you think is best to describe the motion of the object? This one never fails. The average velocity of that object for the entire 6-second interval is 5 seconds. This does not work. The 3.75 meters per second, the simple average of these two values does not work. And again, this question is just to reinforce what we had already said. Unless the object is doing the same thing the whole time, the same kind of motion, the whole time interval, then the simple average can't work. The only time the simple average can work is if you have the same kind of motion happening for the whole interval. We have two different kinds of motion happening. Now, I suppose the other thing that could happen, if you had the two different kinds of motion happening for equal intervals of time, that could work. In other words, if it was 2 seconds at rest and then 2 seconds moving at this pace, then that would be 15 meters. Oh boy. That would be, oh no. Is this not going to work? That would be, oh good. That would be 15 meters over 4 seconds. Like if this doesn't exist, if that's not even there, let's pretend it never happened. Then 15 divided by 4, that is 3.75 meters per second. And so, oh boy. And so that could, the simple average could work in that case because we have equal time intervals. We were at rest and we were moving with 7.5 meters per second of velocity for equal amounts of time. Then the simple average would be correct. But because it wasn't the case, because we had 4 seconds worth of 7.5 and only 2 seconds worth of 0 meters per second, the average is weighted toward 7.5, not down the middle. Hope that makes sense. Okay, moving on. That was page 1. Oh gosh, now I gotta move me out of the way. Gotta get here. Oh gosh, what is happening? Here. Okay, so here's page 2. Get me back up in the corner. It says graphically represent the relationship between velocity and time. Object describe about, oh gosh. What the, okay, described above. Oh, so we just had to make the VT graph. So the first part was horizontal at 0. The second part was horizontal at 7.5. And the size of that rectangle is 7.5 meters per second tall times 4 seconds wide. That is a 30-meter displacement. That's question F. That is the displacement, 30 meters, which is exactly what we said up here. It shows it starts at 0 and ends where? Up here, which is at 30 meters. So we have 30 meters of displacement. We already used that here. So this is just reinforcing with the VT graph, reinforcing the same thing we've been saying. The area under the curve works. All right, now this one. Question 2. You were supposed to answer a few questions. Let's see, I think it was, when is it slowest? When is the object moving slowest? That would be B and F, because the steepness at B is 0. The tangent to the curve is horizontal. The tangent to the curve here is horizontal. Next question, I think it was, when is it speeding up? I think is the question. So when is it speeding up? That's when the steepness of the curve is getting steeper, when the slope is increasing. That's happening from B to D and from F to G. That's when the steepness is getting bigger. And again, use your little pencil or something as a slopometer and follow along the curve, and you'll see, again, if you're going from B to D, it's doing this. It's getting steeper. And then from F to G, it's doing this. It's getting steeper. Steeper, steeper. Even though the line's going down, the steepness is getting steeper. Then the last question, I think, is, when is it slowing down? Well, that would be from the beginning until B. It would be from D to F, and then it would be from G and beyond. That's what I would say. And lastly, now this is some good stuff. So you have a stunt driver apparently testing airbags, not hitting anything, and actually stop. This makes no sense. Applies his brakes and accelerates uniformly to a stop just as he reaches a wall 50 meters away. So he's not even hitting the wall. So this clearly is not an airbag test. I don't understand what's going on. So sketch qualitative. So we have a constant velocity for 4 seconds, and then it slows down. So the steepness has to decrease, going closer to a 0 steepness. So it was steep, now it's not. Now the velocity time graph means, again, it's constant velocity for 4 seconds, and then it slows down as well. So the velocity goes from a positive large value down to nothing. So that's what the qualitative sketches would look like. Then it says, how long did it take for the car to travel the first 100 meters? Well, 100 meters of displacement, again, delta x over delta t here. 100 meters of displacement, delta t we're looking for. 25 meters per second is the average velocity for the first 4 seconds. And so it took 4 seconds to do that. The next question. Area under the velocity time graph equals displacement of the car. How long must the brakes be applied for the car to come to, oh, wait a minute, what happened here? Oh, I think I erased something and did, oh gosh. Here's where things got complicated. And we're right in the middle of something. We're not even done yet. Oh, it was right here. This is what it was. Pay no attention to the red. It's the blue. The red is something else. Here, what we did was, I said, or somebody said in here, that if it's a triangle, if this right here is a triangle on this graph, and the height of the triangle is 25, we don't know the base of the triangle. All right, so again, follow along. We know that this is 25 meters per second tall. We don't know the base of the triangle, but we do know that the area under the curve is 50 meters. That's what the question is saying. It's saying, hey, we know this is 50. We know the height. We don't know the base of the triangle. And so we said, okay, that means the base of the triangle is the delta t. That's what we don't know. We know the height of the triangle, so 1/2 the base times the height. We know it's 25 meters per second tall. We don't know the height or the width of the base, but we also know that the area of that triangle has to be 50, which means the delta t has to be 4 seconds. So I hope that makes sense, that's what that would have to look like. Now this graph, this is supposed to be the quantitative graph, and I totally messed it up. I started to do something else with it after the fact to answer this question. So it should actually look like this. So this would be the first 4 seconds would be the red part. The second 4 seconds would be the blue part there. All right, so pay no attention to this part. This is a separate conversation that I'll probably have in another video. So pay no attention to that. This was constant 25, and then it goes down toward the 0, and it took 4 seconds to do it, and the area under this curve is indeed 50 meters. Half of this rectangle, this big rectangle here, half of that would be the 50 over here. Then the last question was, what's the acceleration provided by the brakes, and how do you know? Well, you can use this, delta v over delta t. Acceleration is delta v over delta t. You changed from 25 meters per second. Again, that's the initial. Okay, so remember, it's always final minus initial. Delta v is always vf minus vi. So it's the final of 0 minus 25 meters per second, and that took 4 seconds. And so the acceleration is actually a negative 6.25 meters per second squared, or meters per second for every second. So that's that. Now we had just started to have another conversation here, which I will save for another video. Yeah, I'll save that for another video. So this was just worksheet 3. We just started another conversation, which I'll do later. But this is at least enough for now. Hope you're taking care. We'll see you later.